Hello everyone, welcome back to the video lecture series of Basic Electrical and Electronics Engineering. In this session, we are going to discuss how the EMF or voltage is generated, what are the conditions required for that, and the laws regarding electromagnetic induction, that is Faraday's first and second law. So let's get started. The term electromagnetic induction is the phenomena of voltage or EMF induction in a conductor which is placed in a magnetic field. Okay, it is a phenomena of voltage or EMF induction in a conductor when it is placed in a magnetic field. And who discovered that? It was first obtained by English scientist Michael Faraday in 1831. Okay, and then he formulated two laws of electromagnetic induction that we are going to discuss here. The Faraday's first law. Okay, the Faraday's first law of electromagnetic induction states that whenever the magnetic lines of force, which is also called as flux lines, which we have already discussed in the previous sessions, the linking with the coil or conductor changes, an EMF gets induced in the coil or conductor. Here, conductor is a state, this line or coil, maybe the conductor is wound in a number of turns, so that will be known as coil. Okay, it says that whenever a magnetic lines of force or flux linking with a coil or conductor changes, an EMF gets induced in the coil or conductor. That means here are three basic requirements for the production of EMF or for the generation of EMF. What are those? First condition is conductor in which the EMF will induce. Okay. The second is magnetic field in which we have to place the conductor. And third, the flux lines linking with the conductor must be changing. That means there should be relative motion between conductor and magnetic field or magnetic flux lines. Here the figure shows that this is the magnetic field, this one is the blue one is the north pole, and this red one is the south pole, and these are the flux lines from north to south. These are the direction of flux you can see here from north to south. And one man holding one conducting wire in his hand, okay, which is insulated one, so he should not get the shock. And here the wire, he is moving the wire or this conducting material from top to bottom. He is moving this conductor from top to bottom, and these are the blue ones are the electrons which are flowing in this wire. Okay, and this is the galvanometer which shows the deflection if there is any voltage in the conductor. Okay, when this man is moving this conductor from top to bottom, what will happen? See here, when the man is moving this conductor from top to bottom, the deflection of this galvanometer takes place. It is the pointer of the galvanometer is displacing here in the right direction, in this direction. Okay, when he stops this movement, what will happen? It come back to zero position as there is no change in the flux lines with the conductor. If the movement is going on, the pointer will deflect automatically. Okay, when it stops, the moment it stops, the pointer also stops at zero position. That means to produce an EMF, three basic conditions has to be fulfilled. First condition, we must have the conducting material in which the EMF is going to produce. The second one is magnetic field in which the conductor is placed. Okay, and we want the linking between the magnetic lines of force and the conductor, but it is changing in nature. That means if suppose we have this conductor and we have this magnet also, but we have put this conductor in the magnetic field only, and there is no movement of either this conductor or magnet, they are both stationary, then in that case the EMF will not generate. The third important condition for EMF to generate is there should be relative motion between this conductor and the magnetic field. That means the flux linking with the conductor must be changing. Okay, let's see the another diagram. Here the first indicates that this is the coil, this red one is this is the circular coil which is placed in this magnetic field, where here is a north pole and this is a south pole. So direction of magnetic field is in this way. Okay, this is the direction of magnetic field from north to south pole. Okay, and in that conductor is placed in a circular way. Okay, here when we rotate the circular coil in this direction, we will rotate the direction in this direction, then current will induce in that coil. Okay, when there is no movement, when the movement is stopped, the current, we will not have the current through this wire, because there is no EMF, so there is no current also. Okay, now see, now the movement is stopped, so there will not be a current. Now if we move the current in opposite direction, this coil is in opposite direction, there is also current is induced, that is EMF is induced, so current will also flow through this wire as it is a closed loop. Okay, when there is no movement, no current. When there is a movement, there is a current. Okay, when there is no movement, no current. When there is a movement of conductor, there is a current. Okay, that means first one is conductor is required, second one is magnetic field is required, and the relative motion between them is required. These three conditions are essential for producing the EMF or voltage in the conducting material. The second figure shows that here we have seen that the conductor is moving here. The magnets are stationary, they are not moving, they are stationary, they are at standstill position, but the conductor is moving here. Okay, in this figure also the magnetic field is stationary, but the conductor is moving. Okay, conductor is moving. In this case also the magnet are stationary, the conductor is moving, here rotating in this direction, then again rotating in this direction to produce the EMF. But what will happen when the coil is stationary but the magnet is moving? Here the second way of producing EMF is we place the coil stationary but the magnet is moving. Okay, in this case also we have to check the three conditions are satisfied or not. First condition is what? We want conducting material, so conductor is there, first condition satisfied. Second condition is what? Magnetic field, we want magnetic field, so that we can place this conductor in the magnetic field. So here we have this magnetic field from north to south pole, so second condition also satisfied. Third condition is what? We want relative motion between magnetic flux and this conductor, so this is achieved by this movement of this magnet. As the magnet is moving, the flux lines linking with this conductor is changing, so that's why the third condition is also satisfied. So we will get the EMF, and here it is indicated by this pointer. Okay, when it is coming inside the conductor. Okay, when it is coming here, see, inside the conductor it goes to positive maximum, when it goes back it goes to negative maximum, and when there is no movement, the pointer stop at 0. Okay, this is indicated by bulb also. When the EMF is will get induced, the bulb will glow. When there is no EMF, the bulb does not glow. Okay, in this way the EMF can be generated. The Faraday's first law states that how the EMF can be generated, how the EMF gets generated, when and what are the conditions for that. There are three conditions. One is conductor, second one is a magnetic flux or magnetic field, and third one is the relative motion between conductor and magnetic field is necessary. Okay, then how much EMF gets induced? If I have this coil, then how much EMF is induced in it? When I change the coil, then what will happen to the EMF? How much EMF we will get? That will stated by the Faraday's second law of electromagnetic induction. Okay, the Faraday's second law of electromagnetic induction states that whenever a conductor cuts or is cut by magnetic flux, an EMF is induced in the conductor. the magnitude of which is proportional to the rate at which the conductor cuts or it cuts by magnetic field. Means what? Whenever there is a conductor which cuts the magnetic field or is cut by magnetic field, that means conductor is cutting the magnetic fields or magnetic flux is cutting the conductor. In the both ways, the EMF is induced in the conductor. Okay, but the magnitude of that EMF is proportional to the rate at which it is cutting the magnetic flux lines or is cut by the magnetic flux lines. That means what? There are three conditions to generate the EMF. Okay, first one is a conductor, second one is a magnetic field, and third one is a relative motion between them. Okay, but the magnitude of EMF induced is stated by this Faraday's second law of electromagnetic induction, which states that the magnitude of that EMF is proportional to the rate at which the conductor cuts or is cut by the magnetic field. That means what? The magnitude of EMF produced is proportional to the rate at which it is cutting the magnetic flux. See this figure. In this figure, these are the conducting material having this 1, 2, 3, 4, 5 to 6 turns. Okay, and this is the magnet, and the magnet is moving from this side to this side. And what is happening here? The pointer is from positive, again negative maximum, and at standstill position. See here, when current induced only on movement or magnetic flux changes, and no movement, no current induced in the coil. As the magnet is moving, here we can see that there is a deflection of the pointer. When it is standstill, there is no deflection. That means whenever the magnet is moving, only EMF get induced, and when there is no movement, no EMF will be there. Okay, and the magnitude of which depends upon this rate at which or the speed of this movement. Okay, the movement or speed of this magnet will decide the magnitude of EMF. It can be expressed as or by this given equation: E is equal to N into d phi upon dt volt, where N is the number of turns of coil, where E is the induced EMF in the conductor, N is the number of turns of coil, d phi is the change in flux, and dt is the change in time. So d phi upon dt will be change in flux with respect to time. So this is the expression for induced EMF. Okay. Now this is the simple AC generator which is used to generate this AC voltage. Here we have a magnet, and within the magnetic field of this magnet, one conductors are placed which are connected to this galvanometer shows the EMF is generated or not. Here the mechanical energy is converted into electrical energy. The mechanical energy is provided to this conductor to rotate with the help of turbine, and turbine is rotated with the help of steam. For example, in case of thermal power plant, and this mechanical energy is converted into electrical energy. This is the simple AC generator to produce the AC voltage. This picture shows how the magnet movement shows the EMF induced in this conductor shows by this galvanometer. Suppose magnet is moving in, we get the right deflection. When there is no movement, no current, so it pointer shows zero deflection, and when it is moving out, it shows left deflection. That means according to the movement or direction of movement of magnet, we are getting the direction of EMF also. Okay, and this picture shows how AC wave is generated. When it is rotated in this direction, the electrons flow and in this direction. When it is rotated in opposite direction, we will get the opposite direction of flow of electron. This is the positive red one, and this is the, we call it as a negative one. This is a total one cycle of a AC supply. We will discuss this AC waveform in detail in the upcoming sessions. Okay. Till then, stay tuned and keep learning. Thank you.